The concept of electromagnetic induction is used in electric generators. Electromagnetic induction is nothing but current flow in a conductor caused due to a changing magnetic field. So how does an electric generator work? Here's a simplistic diagram of an electric generator. These are the two poles of a permanent magnet, and what we see here between them is a rectangular coil ABCD. One end of the coil is connected to the ring R1 and the other end to the ring R2. Now the inner sides of the ring are completely insulated. These two things we see here are stationary brushes which conduct electricity. Let's call them B1 and B2. What do we have here in the center? It's an axle to which the two rings R1 and R2 are internally attached. Now what happens when the axle rotates? When the axle rotates, the ring rotates along with the coil, but the brushes will remain stationary. And the outer ends of the two brushes are connected to the galvanometer, which will tell us if current is flowing in the external circuit. Before we begin with the experiment, let me give you a general idea about what happens in an electric generator. Mechanical energy is used to rotate the axle, which in turn rotates this coil. Because of the movement of the coil and because of the magnetic field, current is induced in this coil. In short, mechanical energy is used to rotate a conductor in a magnetic field to produce electricity. Now, how does it actually work? The axle is rotated from outside to rotate the coil which is in the magnetic field. Say we rotate it clockwise, which means arm AB will move up and arm CD will move down. Now to find the direction of current flowing in arm AB, we use the Fleming's right-hand rule. Do you remember it? The thumb of our right hand gives us the direction of the movement of the conductor, the index finger gives us the direction of magnetic field, and the middle finger gives us the direction of current induced. So we apply to arm AB, we see that the current flows from A towards B. And if we apply to arm CD, we will see that the current will flow from C to D. The induced current will flow in the direction ABCD. What about the direction of current in the external circuit? It will flow from B2 to B1. Now let's stop and see what happens after half a rotation. We see that arm AB is on the right and arm CD is on the left. And the coil is still rotating clockwise, which means CD is going up and AB is going down. So this time the flow of current will be in the direction DCBA. And in the external circuit, it's moving from B1 to B2. And in a similar way, after every half a rotation, the polarity of the current in the respective arms changes. This kind of current, which changes direction after equal intervals, is called as an alternating current, which is why this device is called an AC generator. What if we want DC current? It's easy. We just use a split ring type commutator. It's similar to the one we used in the case of an electric motor. If you notice in this case, this brush is always in contact with the arm moving upwards, and this one is in contact with the arm moving downwards. This produces unidirectional current, and this generator will be called a DC generator. So DC is unidirectional and AC is reversing direction periodically. Which one is used in daily life? Most power stations use alternating current. A very important advantage of AC over DC is that electric power can be transmitted over long distances without much loss of energy.